Okay, we will continue to the second talk today by Qing-Hu Hou, also an old friend of Dawn. We'll speak about log-convexity of P-recursive sequences.
Okay, thank you for introducing. Before we start the math part, I would like to mention our first intersection with Doron. In 2001, Doron was one of the referees of my PhD thesis. He wrote a very warm report. It encouraged me to move on in the field of symbolic computation until now. So I must say thank you, Doron.
You're welcome. It was a very good dissertation.
Okay, today I will talk about the log convexity of P-recursive sequences. It's a joint work with my two PhD students, Dr. Zhang and Dr. Li. We will first introduce the problem, and then we focus on the P-recursive sequences. And by the way, we will also talk about the partition function. So the first question is, what problem we are consider? In fact, we consider the inequalities in combinatorics. In particular, we consider the log convexity. Let A sub n be a sequence if the square of each term is less than or equal to the product of its previous term and the next term. Then we say the sequence is log convex. Here log means we use multiplication instead of addition. And the convex is the same as the euro meaning. On the other hand, if the inequality is greater than or equal, we say the sequence is log concave, or sometimes we say it satisfies the Turan inequalities. Here is a simple example. The few terms of n factorial is 1, 1, 2, 6, 24. And we can see the square of 2 is 4, which is less than 6. And the square of 6 is less than 2 times 24. So the sequence is in fact a log convex. We can prove it by this one line. Since the square is n divided by n plus 1 times the previous one times the next term. So it's less than this one, and the sequence is log convex. If we consider the sequence n choose big capital N choose small n, in fact, it's a finite sequence. The other terms are all zeros. Here is the example for capital N equals 4. We have 1, 4, 6, 4, 1, and it is log concave. We can see the square of 4 is greater than 6, and square of 6 is greater than the square of 4. In fact, we can also prove the log concave because the ratio of these terms are 1 plus something. Here is a positive number. We have more complexity cases. Let phi and psi be the operators given by these two. In fact, if we have if A sub n is a sequence of log convex, then after applying the operator phi, we will get a sequence, a non-negative sequence. If it is concave, after applying the operator psi, we will get a non-negative sequence. As usual, we let the case power of phi be the composition of phi k times with itself. If we apply phi and phi squared up to phi to the rth power, we get all non-negative sequences. We call the sequence A sub n is R log convex. Similarly, if we apply the operator psi and we get all non-negative sequences, we will call it R log concave. We also have the higher order Turan inequalities, which involves 4 terms. So the next question comes, why we started these properties? A simple answer is they are interesting, but it doesn't help if when you apply for a grant. Fortunately, we have a good reason, because it is related to the famous Riemann hypothesis. In fact, Riemann hypothesis is equivalent to the real rootness of certain Jensen polynomials. And real rootness implies the higher order Turan inequality. See these 2 papers. In fact, first Biu-Chen proved that the partition function is satisfy higher order Turan inequalities, and this lead to the next paper, which connect the real rootness, the Jensen polynomial, and the real Riemann hypothesis. Now the third question comes, how can we prove these inequalities? We have several methods. We have algebraic method as done by Brandon and Professor Liu and Wang. We also have analytic method as done by Biu-Chen. But I like most is the computer proof as done by our previous speaker, Manikavas and Pete Pauly. They gave a computer proof on the log concavity of the small polynomials. Our approach is almost the same. We want to prove the R log convexity or concavity by aid of a computer. Still, we use the same frame, that is guess and check. I find that the organizer is quite right to put these 2 talks together. We all use this process. So first, we need to guess an upper bound and a lower bound for this ratio, because this ratio plays an important role in proof the convexity or the concavity. If the ratio is greater than 1, it is log concavity, convexity. And if the ratio is less than 1, it's log concavity. So next step, we need to show that they are really the bounds. And there's one more step. We need to find the relation between the ratio of the original sequence and the sequence obtained by applying the operator psi or phi. With success in these 2 kinds of sequence, one is the P-recursive sequences, and the other one is the partition function. So let us first consider the P-recursive sequences. As we know, a P-recursive sequence is a sequence satisfy a recurrence relation with polynomial as coefficients. Here, p sub n, p sub 0 of n, p sub 1 of n, up to p sub d of n are all polynomials in n. But how to give an upper bound? How to guess? We need the asymptotic behavior of.
Excuse me,
this.
just checking. This is the same as saying the generating function is definite or holonomic, yes?
Yeah, that's
Okay.
quite right. So we say our two, my talk and the previous one intersect a lot. So we also need this result as used by Manuel. He used just one term, but here we need more terms. We have this result for a P-recursive sequence. The asymptotic form is a linear combination of this form. It's e to the q and multiplied by s. Here q involves n log n and power of n, and s also involves log n and n's power. It was first approved in 1933 and recovered by Doron in 1985. And recently, Doron has used it to give the to implement it in Maple, and Manuel implement it in mathematics. Now with this asymptotic expression, we can prove this result, which gives the form of u sub n, the ratio. It must be 1 plus something. Here is the rational function of log n divided by n to the alpha's power. In fact, alpha is just here. It's the same as here. Of course, we can order them in increasing order. Here is an example. Let I sub n be the number of evolutions on 1 up to n. We have this recurrence relation. And by the implement of Doron or Manuel or myself, we get this one. Here is C, is a constant. In Doron's paper, he need to compute C, but here we does not need to compute C because we consider only the ratio, and the constant unlimited. So if we get this one, we can prove that u sub n have this asymptotic expression. Similarly, if we divide it by n factorial, we will get this expression. From these two expressions, we can see that the inversion number must be log convex for n large enough, because for n large enough, this one is greater than 1. And also for n large enough, if I divide it by n factorial, it must be log concave. But to prove the inequality, we need bounds, not only the asymptotic behavior. So we need to guess the bounds. How to guess the bounds? We start from the ratio of two consecutive terms. Also need we use the asymptotic expression of a sub n. We can see it from this example. Like let m sub n be the nth Moskine number. Then we can compute. It has this asymptotic. And then the ratio here, we cancel the constant and get this expression. So how to give a bound? Just minus 1 divided by n squared and plus 1 divided by n squared. So we get this one, f sub n, as the lower bound, and this one, g sub n, as the upper bound. Just a plus minus 1 or plus 1. Now, here is the guessed bounds, but we need to prove this bound really works. The key point is we have the induction step. We can show that if f sub n, f and g are the bounds for r sub n, then for it also the bound for r sub n plus 1. Now let's look at an example. We use the recurrence relation. Here is the recurrence relation for the Moskine number. And we change it divided by m sub n and change it to r sub n. We get this one, and then we get r sub n plus 1 equals this one. Now we have an upper bound of r sub n is g sub n. So we have this inequality. And if this one is greater than f sub n plus 1, we will get this one. And this is quite right, but we need n large enough. Why n is large enough? This one is a rational function in n, and this one is also a rational function. And if we compute them, we will find the leading term is positive. The difference of these two terms, the leading term is positive. And but we need to check the large root. The large root is about 74. So we require n is bigger than 75. In a similar way, we can prove if R is bounded by f sub n and g sub n, then R n minus r sub n plus 1 is bounded by f sub n plus 1 and g sub n plus 1. Once we have the bounds for R, we then have the bounds for u sub n. And also, so the next step is to connect the original sequence and the sequence apply the phi. In fact, we have this relation for the ratios. So we just need to follow this process. We have the bounds for R, which implies a bound for u sub n, and then a bound for u sub n, but for the new sequence and up to R. Finally, we need to prove this one is greater than 1. Then the sequence A sub n is R log concave, R log convex. If this one is less than 1, and each one is less than 1, we will deduce that the sequence is log concave. Also, we implement it in computer. Now here's the recurrence relation for Moskine number. We use n, capital N, and denote the shift. And we input the initial values and the the R. Here we want to prove 2 log convexity. So we need the asymptotic of a sub n up to 5 terms, n to the 5/5 power. And here is the computer generated proof. To prove this 2 log convexity, we need the ratio to be this bounded by these 2 terms, and the sequence, the first ratio u sub n must be bounded by this one and this one, and this would imply that the 2 log convexity. Of course, we need to compute the minimal n such that this equality holds. We find that we also this process also works for the partition function, but this time we need the Hardy-Ramanujan Rentmecher formula and the error estimation given by Lemma to derive an estimation for P of n. In fact, P of n contains 2 parts. T of n is the main part and R of n is the error part. We have this estimation. The error part is relatively small. We can see that U of n is almost approximately square of n. And the error part is just exponential small. Okay. So
באתי לראות שהכל בסדר והכל עובד לך. כן? סבבה. אם אתה צריך אותי, אני לא.
okay, with this estimation, we can give the estimation for the ratio of this ratio up to any accuracy. Here, I just show the the estimation up to z to the 5th power, where z is just a mu of n. Okay, why we use this? Here is the main part. Here is the lower bound, so we need to minus this one. And here is upper bound, we need to plus this part. And here, this number is the minimal bound such that this holds. So with this estimation, we reproved the theorem of Chen and his co-author, which leading the Riemann hypothesis. The proof P of n satisfy the higher order Turing inequality, but they use the estimation up to z to the 10th power. We find to the 5th isn't enough, and the proof reduced to 1 page from maybe 20 pages. Okay, that's all. And happy birthday to our 2 respective professors.
Thank you very much, Qing-Hu, for the interesting talk. No questions?
Yeah, I have a first quick comment. The Moltke numbers are also dear to Amita Regev. One of my favorite interpretations of Moltke numbers was first found by Amita Regev. It's the number of young tableaus with 3 rows and n cells. That's one of my favorite results. So it was relevant also to Amita's work.
Yeah, I need to add this.
Yeah.
And the other comment, it's really exciting how you can manipulate with a computer inequalities. And you gave me some hope for my old dream. The problem with the so-called WZ theory, that to prove, for example, the Roger-Ramanujan identity by computers, you need an extra parameter. But if you just take the original Roger-Ramanujan identity in Q series, it's 2 Q series. So you look at the partial sums and you look at the difference. So it satisfies some recurrence. It's Q P-recursive. It satisfies some easily found recurrence. So you have to prove with these particular initial conditions that it goes to 0. Alas, if you use the naive asymptotics, you don't get it. But with your beautiful approach, I think there's hope to mechanize this part. That'd be really great. So you gave me some hope. Thank you.
Thank you. I will try it.
There is you started with IN, the number of involutions. Then Motzkin number is the number of involutions is like number of standard Young tableau of 2 rows. Then you have number of standard Young tableau of 3 rows. You have now you have also formulas for number of standard Young tableau of 4 and 5 rows, like products of Catalan numbers. So the number of the involutions, the number of all standard Young tableau. Number of 2 rows is Catalan. The number of 3 rows Motzkin. Number of 4 rows is product of 2 Catalans, if I remember correctly. And there are papers also about number of 5 rows and algebraic proofs, combinatorial proofs. So these numbers also should, maybe you can prove for any Bowden number of rows that this log-convexity holds.
Yeah. Thank you. I will check.
I have just a question, maybe a comment. Take a polynomial or a generating function for a finite sequence. The coefficients are an in this polynomial. And now there is this suspicion that if you raise the polynomial to higher power and look at the coefficient sequence, then it will eventually be highly log-concave. So maybe you can consider addressing this type of anticipation.
Yeah, it's interesting. Maybe you can send me some reference about it.
Yes, I can do that.
Okay, thank you.
Any more questions? So if no, thanks the speaker again.